This screencast is going to focus on the idea of what's called limiting reactants and answer the question, why do reactions stop? So the previous problems that we've worked out have given us one amount of reactant and asked us to find how much product can be made. If there were other reactants, we assumed that those were in excess, which means we just assume that we have plenty of it, and then that way we didn't have to take it into account when we were figuring out our products. But if you think about a reaction being like ingredients when you're making a cake or making chocolate chip cookies or something like that, you can't just have a certain amount of one reactant or ingredient. You have to have the right amounts of all the ingredients in order to make a certain product. So you may have a ton of flour in your house, enough to make 4 cakes, but you may not have enough eggs, and so the eggs would limit the amount of cakes that you could actually make, and your flour would be excess or leftover at the end. So we start with a scenario that I give you here, and usually students do this in class. They find out that I'm going to take early retirement and, hand weave baskets and make gift baskets for a living. But here's the idea. I've given you a recipe for my gift basket. Obviously, every basket's going to include 1 basket. I'm going to put 3 chocolate bars in, 1 book, 2 coffee mugs, and then 3 packs of cocoa mix. So if this is my inventory, and I wanted to figure out how many possible baskets I could make, I'm going to do that based on each individual ingredient for this gift basket. So the first one's pretty easy. If I say, well, I have 28 baskets, and I divide that by the recipe, which is 1, then 28 divided by 1 just gives me 28 baskets. So based on baskets alone, I could make 28 gift baskets. Now chocolate bars, I need 3 chocolate bars for every basket. So if I start with 80 and I come in and I divide that by 3, we'll do 80 divided by 3, you get 26.7. Now you can't have a part of a chocolate bar, so we would just round that to 26. So based on chocolate bars, we can make 26 gift baskets. All right, based on books, there's going to be 1 book in each basket. So again, a pretty easy calculation. Based on that, I can make 25 gift baskets. Coffee mugs, I want 2 in each basket. So I'm going to divide by 2. 52 divided by 2 gives you 26. So based on mugs alone, I can make 26 gift baskets. All right, and then last is my cocoa mix. 82 packs is what I have. I want 3 packs per basket. So if I do 82 divided by 3, I get 27.3. And again, I can't really have a part, so I'm just going to round that to 27. So what we did there to figure out the number of baskets possible was we took what we had, our inventory, and we divided it by the amount that went into each basket. And if you think about a chemical reaction now, we've got reactants forming products. Remember we said that these coefficients, these numbers out in front, equal our mole ratios. Okay, so we're going to move into reactions in a minute. So if I come down here and I answer the questions, it says, well, how many gift baskets can I make based on the first column? Well, potentially 28, 26, 25, 26, 27. So based on the limiting factor, which is my books, I can only make 25. I have to take the lower number, because just like the flour example with the cake, just because you have a ton of flour doesn't mean you can make a bunch of cakes. You've got to have all the reactants or ingredients in the right amounts. So then the second question says, well, what item will I run out of first? And if you notice, we can only make 25. After that point, if we try to make this 26th basket, we're not going to have a book to put into it, right? So the item that we run out of is the books. And then it says how much of each item will be left over after she makes the number of baskets indicated in your answer to number 1. So let's think about how we can do this column. If I make 25 baskets, now I need to look at my recipe and say, okay, for baskets, if I have 25 baskets that I need to make, and each gift basket takes 1, then I would use 25 baskets, right? To get the leftover, I would say the inventory, which was 28, minus 25, and I would get 3. All right, for chocolate bars, each basket needs 3. Again, I'm making 25, because I'm limited by the books. So that will use 75 to get my leftover. Oops, wrong number first. To get my leftover, I start with my inventory, subtract what I use, and I would have 5 left over. For books, I know that I'm going to use all 25, and I'm going to have 0 left over. Alright, for coffee mugs, if I make 25 and each basket takes 2, I'm going to use 50. My inventory was 52, so I'm going to have 2 left over. And then for cocoa mix, if I make 25 and each basket takes 3, I'm going to use 75. I started with 82, so 82 minus 75 gives you 7 left over. So you notice that the thing that limited us is the thing we have 0 of, and that's the definition of a limiting reactant. Now, question 4 says, why can't she continue to make gift baskets after she runs out of the item from question 2? Well, for this case, could I potentially make a basket out of the basket and the chocolate bars and the cocoa mix and the coffee mugs that I have left? Sure, but it doesn't meet the recipe, right? We ran out of books. But for a chemical reaction, could the reaction keep going? And the answer is no. If you don't have, a reactant anymore, you can't convert it to products. So if we get a good definition for limiting reactant and excess reactant, a limiting reactant is the reactant that runs out first in a chemical reaction and determines the amount of product that can be formed or made. So it's the critical one because it's going to tell us how much product can be made. In our example up here, we ran out of books, and so because of that, the gift basket making stops because we don't have any more books. Now, excess reactant, if we look up here, all these that we had leftovers of, those would all be considered excess reactants. So it's the reactant that remains after the reaction has gone to completion. So the reactant that remains after the reaction has gone to completion. Alright, so we abbreviate those LR and ER, and you'll see those popping up. And if we kind of look at one of our stoichiometry questions here, this is what I mentioned at the beginning of the screencast. If you don't see that they're talking about an excess of reactant, and they've given you 2 amounts of reactants or sometimes 3 amounts of reactants, then you have to test to see which one is your limiting reactant. And I'll show you how to do that on the back side of this worksheet. But sometimes they won't say, hey, remember to test for limiting reactants. You just have to know that if they've given me 2 amounts, then I'm going to have to test for both. Alright, so here's an example. If we have 5 moles of magnesium and 3 moles of oxygen, how many moles of magnesium oxide could be made? So there's my skeleton equation. Remember that oxygen's a diatomic. We balance this because it's 2 plus and 2 minus, and then we come and we balance the equation. And now we've got our synthesis reaction. So let's think about this. If we have 5 moles of Mg to start and 3 moles of oxygen to start, they want to know how much I could make. Alright, well let's kind of go back to where we were before. If we have 5 moles of Mg, and let's say they didn't mention anything about the O2, so we'll just pretend that they didn't even mention it. If I want to figure out how much MgO could be made, then I look at the mole relationship, and it's 2 to 2, right? So for every 2 moles of magnesium, I can make 2 moles of MgO. So this, based on just the magnesium, you can make 5 moles of MgO. So that's checking the Mg. Now let's check the O2. The O2 has 3 moles. So now let's pretend that Mg is not a problem, and let's look at the O2. So for this mole ratio, it's 1 mole of O2 makes 2 moles of MgO. So if we do 3 times 2, we get 6 moles of MgO. All right, so again, just like with the baskets, you know, magnesium's willing to make 5 moles, oxygen's willing to make 6 moles. As much as we would love for this to happen, it doesn't happen. We have to take the lower amount. And the reactant that produces the lower amount is called our limiting reactant. So that means that our LR here is Mg, and our ER, or our excess reactant, is O2. So it can be a little deceiving because sometimes students look and they say, oh, well, that has 5 moles and this has 3 moles. That's less, so O2 must be limiting. But it's not just about that. It's about the mole-to-mole ratio as well. So I'm going to show you a method for solving for limiting reactants that I think works really well. And they're called BCA tables. And we're going to go through probably just one of these. And then I might swing back in another screencast and do some more examples. All right, so the first group, they've been balanced for you. The second group, they just haven't been balanced, so there's really no difference. We're starting in moles, and so BCAs, the B stands for before, C is change, and A is after. So what we do is we come over and we take our givens, and just like we did with our inventory, we took our inventory and divided it by the recipe. So I'm going to do 16 divided by 4, and that's going to give me 4.00. And then I'm going to do 9 divided by oxygen's coefficient, which is 1, and I get 9.0. This is going to give us our x, and here's what we're going to do. X is going to be equal to the lower number. Now don't freak out because you see an x. We're just going to use it based on this ratio over here. All right, so obviously 9 is bigger than 4, so that means our x is 4. That means this is going to go down by 4x. The O is going to go down by just x because its coefficient is 1. And then the Na2O is going to go up by 2x. So the first thing I do for my before, I don't have any product at the beginning of the reaction, right? I have 16 moles of Na. I have 9 moles of O2. All right, because the lower number came from the Na, guess what that means about Na? Na is our limiting reactant. And that means Na is going to be completely used up. So this is going to go down by 4x, and x is equal to 4. And when you do 16 minus 16, you get a big fat 0, right? So this went down by 4x. The oxygen's just going to go down by x. So this is going to go down by 4. And 9 minus 4 gives you 5. And then this is going to go up by 2x. So 2 times 4. So this is going to go up to 8.00. So this is our after, and it's really nice because it gives you a nice little picture of what's going on. No Na remains after the reaction is over. 5 moles of O2 remains after the reaction is over. And 8 moles of Na2O is formed. So we've answered every single question. We've determined the LR, we've determined the ER, the amount of product formed, and the amount of excess reactant left over. All right, we have time for one more, and then I'll let you try them. So let's look at B. So remember our strategy, we're going to take our given and divide it by the coefficient. So we get 5.00 there. We're going to take our given, divide it by the coefficient. We get 4.00 there. We take the lower numbers. We cross this one out so we're not tempted to use it. That means that's our x. The one that gave us our smallest x is our limiting reactant. So the limiting reactant is HCl. All right, we set up our table. We've got 10.0, 24.0. These are both zeros. This is going to go down by 2x, so 2 times 4. This is going to be completely used up. How do we know that? Because he gave us the smallest number when we divided. And by definition, your limiting reactant is completely consumed. So that's going to give us 0. This is going to go up by 2x, so 2 times 4. And then the hydrogen is going to go up by 3x. All right, so if we do 10 minus 8, we get 2.00 of the aluminum remains. That's our excess reactant. For AlCl3, we get 8.00 moles. And for hydrogen, we get 12.0 moles. So that would be how much is formed.